Hello friends, you are watching Arudire Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, we know that in finite element analysis we are trying to achieve perfect results based on discretization. Better is the mesh, better is the results. So in our today's problem, we'll try to analyze a very specific and very simple problem using finite element method, and initially we'll try to get the analytical solution, then based on different types of discretization with ANSYS mechanical MPDL, we'll try to achieve the perfect results. Let us see the problem. It is a model, it is a tapered bar which is having left hand side diameter 40 mm and right hand side diameter is 20 mm and length is 200 mm. And at the extreme right end we are applying a load of 10 kN. So first of all, what I will do is discretize the model into 8 different elements, and we'll try to find out stresses on each different element and displacements occurring at different nodes. Our aim is to see displacement of the tip, that means the final node at this location, for different types of discretization. So initially we'll make the model into 8 different elements. Next case it will be 4 numbers of elements, then 2, and finally we'll discretize into 1 element. And each case we'll find out the value of displacement at the tip. Next to that we'll get the plot of all these tip extensions with numbers of elements and see whether this value is matching with our analytical value or not. You can see the analytical formula is delta equal to 4PL divided by pi d1 d2. If we apply the existing data in this expression of delta, we can get the actual extension equal to 0.2387 mm. Let us consider this one up to 0.238 mm. Okay. Next to that, we'll use ANSYS mechanical MPDL and discretize the model into 8 numbers of elements, 4 numbers of elements, 2 numbers of elements, and 1 number of element. And each cases we will try to find out the extension of the last node and the tip node, and by the same time we will try to find out the stresses developed in each element. Okay, so let us start our analysis using ANSYS mechanical MPDL. Initially we will create a directory in the desktop. Let us create the directory by the name of ANSYS. Next, we will change the directory to the desktop folder. File, change directory, ANSYS folder. So we'll start from pre-processing. It will be a structural analysis, so we'll check it. Then pre-processing elements, the element to be defined now. Let us add the element to be beam, and by default it is taking 3D finite string we are considering. Element reference type number is 1. That is very important. We have to remember this element type reference number. There is 1. Okay. Close it. Next to that, we have to provide material properties. Material models, structural, linear, elastic, isotropic. Isotropic means material property remains same in all directions. X, Y, Z, all directions, material property will be same. From the data we got that modulus of elasticity equal to 20 gigapascal. If we convert this one, it will be 2E4. And Poisson's ratio it is not given. Let us consider Poisson's ratio to be 0.3. So we provide the value of modulus of elasticity to be 2E4. That is 2 into 10 to the 4 Newton per millimeter square, and Poisson's ratio to be 0.3. Okay. Let's close it. Next to that, we will select sections. It will be coming from beam, common sections. We are having circular profile. You can select from here the circular profile, and let us put the name of this circular profile. On the left hand side, it will be big circular area, so we can consider this one as big circular cross-sectional area of radius equal to 20 mm. As the diameter was 40 mm, so radius will be 20 mm. Let us preview that. Okay, apply. Next to that, on the extreme right hand side, you have to provide another diameter of 20 mm. That means radius will be 10 mm. So we can change the ID number from 1 to 2, and we can rename this one as small. You can select the property from here. It will be circular profile, and radius of this one will be 10 mm. Let us preview this. Is okay. It is a circle of radius 10 mm or diameter 20 mm. So okay, let us close it. Next to that, we have to select tapered section, because that extreme left hand side section and extreme right hand side section to be added in the form of a tapered section. So we can select from here by XYZ location. We can rename the section as tapered 1. We can rename this tapered 1. And the beginning location of the tapered section is at the origin only. So this one should be 0, 0, 0. By default, it will take 0, 0. We need not provide. And the ending section should be at a distance of 300 mm, because total length of that bar is 300 mm. So the ending section will be at a distance of 300 mm. Okay, done. Next to that, we have to model that object, and we are trying to model this one using nodes. So it will be started from create nodes. In active coordinate system, we will be creating nodes in between 300 mm. 8 numbers of elements will be there. That means in between each element there will be 2 different nodes, right? So let us create that nodes in active coordinate system. First one node will be created at 0, 0 location at origin, and the node numbers will be created automatically. We need not provide those node numbers. We have to provide the location of the nodes only. As it is a one-dimensional problem, so we need not provide the values of y and z coordinates, only x coordinate is enough. First node will be created at origin, so we are not providing any value. By default, it will take the origin location. Apply. That means first node is created. Next one, second node will be created at a distance of 37.5 mm away. Apply. Second node is made. Next one will be 75 mm away. Apply. Third one will be 75 plus 37.5. That means equal to 112.5. Apply. Next one will be 150 mm away. Apply. Next one will be 150 plus 37.5, that is 187.5 mm away. Apply. Then next node will be 225 mm away. Then 8th node will be 225 plus 37.5, that is equal to 262.5. Apply. And the last one will be 262.5 plus 37.5. This one will be at a distance of 300 mm away. Okay. So we created 9 numbers of nodes, and the distance between each node is equal to 37.5 mm. Right. Next to that, you have to create the elements. Let us see the elemental attributes. We have to create the section number as tapered 1, because left hand side we are in big cross section and right hand side is smaller cross section, and we have created another cross section that is named as tapered 1. So select the tapered 1 from here, and that to be connected in the form of lines, as a straight line that will be connected. So the section number is tapered 1. Okay. Now you have to connect these different nodes in the form of elements that will be obtained from auto numbered through nodes. You can select the nodes one by one, and that can be connected. Apply. First one is done. Second element applied. Third element applied. Fourth element applied. Fifth element applied. Sixth element applied. Seventh element applied, and the final element added together. Okay, so we got all the elements added together. And we need not go for discretization because we have already created nodes. As nodes are created, we need not go for meshing or discretization. So we made 8 numbers of elements and 9 numbers of nodes, because in between each element we are having 2 different nodes. Okay. Next to that, we have to go for boundary conditions. We have to apply load and that will be fixed from left hand side. So we can go for solution analysis type. It is a new analysis and definitely it is a static structural analysis. Okay. Then define loads. Apply structural displacement on nodes. We have to fix the left hand side. So we have to select that node. Okay. And all degrees of freedom should be selected. That means it is restricted to move in all directions and the value of this one should be 0. If you don't provide any value, that will take by default 0 value. That means the left hand side node is restricted to move. It cannot move in x, y and z direction. That means it is fixed at the left hand side. Okay. Next one, you have to provide a load of 10 kilonewton at the extreme right side. Force moments on nodes. Let us select that node, the extreme right hand side node, that is 9th node. Okay. And Fx means direction of load in the x direction and the value of load equal to 10 kilonewton, that is 10,000 newton. Okay, done. So it is indicated by red arrow. That means at the extreme right side on node number 9 we have applied a load of 10 kilonewton. Next one, we have to go for solution. We have to check whether the solution is okay or not. Right? Let us solve it. Current tell us if everything is right, it will show solution is done. Okay, let us see. It is showing solution is done, so our solution is okay. Now we can see the results from the general post processing. Starting from general post processing. Initially, we have to create the elemental table. Let us create it. Define table. Nothing is defined, so we have to add it, and we can write this one as stress. Stress is our not main criteria. Our main aim is to find out displacement and the extreme right hand side tip, but we are trying to get stresses also at different elements. You can drag it and select the lowest position, that is by sequence number, and from right hand side select LS, and we can remember that at the initial level, in pre-processing step, we selected the element reference number is 1, that will be provided here. Element reference type number is 1. Okay, close it. Next, we can see our results from plot elemental table. Let us see the stress values. This showing at different elements, different stresses are developed, and the maximum stress is actually at the extreme right hand side is 28.2183 Newton per millimeter square or megapascal. So extreme right hand side is having maximum stress. Okay. Now we can see the same thing using list elemental table. That means the same results can be viewed in the form of numbers only. List elemental table. You can see the stresses. We got different elements at the extreme right hand side. On element number 8, we got the maximum stress developed as 28.218 Newton per millimeter square. Maximum stress is 28.218 megapascal and minimum is 8.486 megapascal. Minimum is developed at the extreme left hand side and maximum extreme right hand side. Okay. Next to that, we have to see our displacement and different nodes. We have to find out displacement at different nodes. Right? So we'll go for plot results. Excluding that one, we can see the deformation of the object also. You can see deformed shape, and we can see deformed plus undeformed. That means it will show the actual model together with the deformed model. Let us see that. Okay, you can see the white portion is the actual model and the blue part is the extension of that model. We can see this in the form of like isometric view also. Let us check it isometric view from here, and from plot controls you can change the options from style, size and shape, and display of element should be on. Now see the model. Now each different nodes we can have some kind of extension. You can see this is the extension or elongation at the second node. You can see at different nodes. This is the first node, second node, third, fourth, and this is the extreme right hand side node, ninth node. On a different node, we are having different types of extensions. First node is having 0 extension, and the last node is having maximum extension. Right? You can see this is the second extension, third, fourth, fifth, sixth, seventh, eighth, and this is the ninth extension. This is the elongation for the extreme right hand side node or the tip. The tip has got extension of this much. Now I want to see these things in the form of values. So that can be obtained from contour plot. Nodal solution. You have to see DOM solution, x component of displacement. You have to see the results in the form of x direction because we apply the load in the x direction only. Okay. You can see the maximum displacement at the extreme right hand side is 0.2383. So which is exactly equal to our analytical value. Analytically got the value equal to 0.238. So it is exactly same when we discretize the model and got 8 numbers of elements. In that case we got the final value of the extension of the extreme right hand side tip equal to 0.238 millimeter. Okay. You can see other things also, like from here you can see stresses elemental solution. Let us see von Mises stresses also. This is not our interest. Anyhow, you can see the von Mises stress developed at different elements also. You can see the different elements are having different types of stresses developed, and the extreme right hand side the maximum stress is 28.2183 megapascal. Okay. Our aim is to find the value of the extension at extreme right hand side node. So that can be viewed from list results. Nodal solution, DOM solution, x component of displacement, that means the displacement in the x direction by the application of 10 kilonewton load. Let us see that. These are the values of extensions. We can see the maximum displacement at the 9th number node, it is 0.238 millimeter. We can save this part, file, save as desktop in a folder ANSYS. You can save it. We can save it by the name of 8 elements. Save it. Close it. Next to that, we have to discretize the model with 4 numbers of elements. Okay. So what we'll do is we'll change the orientation of the model, and from plot controls we'll change the style. It will be size and shape. You can see the display of elements should be off. This is the original model. Next one, what we'll do is we'll delete the element, and let us go back to the model again. We will delete the elements, pick all, elements are deleted. Now you can see the nodes, plot nodes. You can see it is 8 numbers of nodes. Now we want to discretize the model with 4 numbers of elements. So the some numbers of nodes to be deleted. And there is some in between nodes. Let us delete alternate nodes in between. Deleted. Plot, we can see we are having 5 numbers of nodes. That means in between we are having 4 elements. This is element number 1, 2, 3 and 4 elements are there. With 4 elements, again we'll repeat the analysis, we'll see the results again. Okay. So we have to create the model again. you have to go for elements and select the element attributes. Let us select the element attribute to be tapered one, what we selected before. Okay. Next one, it will be connected in the form of lines by using elements, auto numbered through nodes. You can select the nodes 1 and 2, apply. First element is made, second one applied, third one applied, then the final element. Okay, we got 4 numbers of elements, and in between we are having 2 nodes. So 5 nodes created and 4 node elements are there. So as the object is ready, we need not go for discretization because the nodes have already been created. You have to apply the boundary conditions, and that will be obtained from solution. Analysis type, it is a new analysis and it is a static structure analysis. Define loads, apply structural displacement on nodes. Let us select the extreme left hand side node. Okay, and we have to fix that node. That means all degrees of freedom should be happy and should be provided 0 displacement. By default it will take 0 value. Okay, that means left hand side node is fixed. Now on the extreme right hand side you have to apply a load of 10 kilonewton. Force moment on nodes. Let us select the extreme right hand side node. Okay, and force is applied on x direction and its load is 10 kilonewton or 10,000 newton. Okay, load is applied. Next to that you have to solve it. Solve, current LS. Okay, if everything is right it will show solution is done. So our solution is okay. You can see our results from here. General first processing, we have to create element table, define table, add the table. You can denote this one as stress, and by dragging this one you can select the lowermost portion, that means by sequence number, and from right hand side select LS and element reference type number should be 1. Okay, let us close it. Now let us see the stress values. Plot element table stresses. As we got different numbers of elements, stress values are also changing. The maximum stress value is equal to 25.17 megapascal and minimum is 9.06 megapascal. Let us see the listed value of this one. You can see the maximum value of stress is 25.17 megapascal and minimum is 9.06 megapascal. Next to that, we'll see the displacement values from plot results. We don't want to go for deformed shapes because we have already seen that. Directly we'll see the nodal solutions. X component of displacement. You can see the maximum displacement is 0.236 and minimum is 0 at the extreme left hand side. You can see this in the form of listing results also. Nodal solution, dual solution, X component of displacement. You can see the maximum displacement is 0.236 millimeter at the extreme right hand side and the minimum is 0 at the extreme left hand side. You can save it. File, save as element 4. As we divide into 4 numbers of elements, you can save it by the name of element number 4. Save it, close it. Next to that, we have to divide this one into 2 numbers of elements. So what we'll do is, we'll go back to the model, plot elements, or we can go for plot nodes. These are the nodes, and first of all we have to delete the elements. We have to clear the different elements. So we'll go back to the pre-processing part, modeling, and we have to delete the elements. delete elements. You can select all the elements, pick all elements are deleted. Next we have to delete the node numbers, because we have to make this object to be divided into two different elements. So we can delete nodes, deleted plot report. You can see the actual nodes. Now we can see it is having three different nodes, and in between three different nodes we are having two elements. Next to that we have to create that elements, and before that element attributes to be selected. You can select the tapered one as the section. Then the elements should be connected in the form of lines. So auto numbered through nodes, select first node and second node, apply. Now the second node and third node. Okay, so we made the model and discretized into two different elements, element 1 and element 2. In between these two elements we are having three different nodes, right? Next to that we have to solve it. Discretization is not required as we have already created nodes. Starting from solution, analysis type, it is a new analysis and definitely it is a static structural analysis. Okay, so define loads, apply structural displacement on nodes. We select the extreme left hand side node, okay, and it should be fixed from XYZ directions, and the displacement value of this one should be 0. By default it will be taking 0 values. Okay, so the extreme left hand side is fixed. Next to that we have to apply a load of 10 kN on the extreme right hand side. Force moment on nodes, select the extreme right hand side node, okay, and it will be 10 kN or 10,000 Newton in the X direction. Done. So we have applied a load of 10 kN at the extreme right hand side. Next to that we have to solve it. Solve current LS. If everything is right, it will show solution is done. Okay, solution is done. Now we can check our results from the general first processing. General first processing, again we will make the elemental table. It is not necessary because our aim is to see that displacement values only. So element table will not make. We have to go for directly plot results. We have to see the deformations in the X direction. Can do plot nodal solution, X component of displacement. You can see the displacement, maximum displacement is occurring at the extreme right hand side. It is 0.230 millimeter and minimum is 0 at the extreme left hand side. We'll see the least results. Nodal solution, X component of displacement. You can see the maximum displacement is at the extreme right hand side node and it is 0.230 millimeter and minimum is 0. You can save this part, file, save as. We'll save this one as element 2. Close it. Next to that we have to make that model as a single object only. That means we have to create only two nodes. Okay, we'll see the results when the object is made with single element only. So as usually we'll select from here plot nodes. These are the nodes, and again we have to select a different element. So we'll delete the previous elements. That can be done from pre-processing part here, modeling. Then you can delete this, delete element. You can select all the elements, pick all the elements are deleted. Next one we have to delete the intermediate node, that means the middle node that we deleted. Delete nodes, select the middle node. Okay, that node is deleted. That can be viewed from plot replot. You can see two nodes are there. There is the extreme left hand side node and it is the extreme right hand side node. Within these two nodes, we will be having only one element, right? So we have to start modeling from here. Create elements, and again element attributes. It will be the previous one. It will be tapered section we are selecting. Okay, then the nodes to be added in the form of elements, auto numbered through nodes. You can select the node number 1 and the last node. Okay, the element is ready. So next we have to solve it. Solution, analysis type, new analysis. It is a static structural analysis, and we have to define loads. Displacement, structural displacement at the extreme left hand side should be 0. Displacement on nodes, you can select the left hand side node. Okay, and it will be restricted to move in XYZ direction. So displacement in all degrees of freedom should be 0. By default it will take 0 values. Okay, so the left hand side is fixed. Next to that we have to apply load on the extreme right hand side. Force moment on nodes, select the extreme right hand side node. Okay, and in the X direction we are applying a load of 10 kN or 10,000 Newton. Okay, next we have to see the solutions. Solve current LS. Solution is done. So we can see our results from general post processing now. General post processing. We don't want to see our stress values directly. We want to see our displacement or elongation. So we start from nodal solution here. Do of solution A, X component of displacement. You can see the list results it is showing the maximum displacement is at the extreme right hand side, that is 0.212 millimeter, right? So this one we can save it, and finally we will plot all these displacements and see when we got our convergence criteria. File save as. Let's close it. So from analytical results we got the value of the extension at the extreme right hand side tip. It was 0.238 millimeter, and again when we discretize the model with the different numbers of elements, and you can see that when the element number is 8, in that case we got exactly same numbers of elongation at the extreme right hand side, and when the element number is very less, in that case we got different results. Now all these results we can plot in Excel and see how the tip values are changing with different numbers of elements. Let's open one Excel file and we can plot all this data. Suppose this is element number and this one extension or elongation. We have different element numbers, this 1, 2, 4 and 8 elements numbers we made, and based on that you can point those values of extensions. You can see the extension values from the saved folder and save it to Excel. Now let us plot these things and see how it is varying. You can select these things and insert graph. You can select the graph from here. Let us select this part. So you can see this value is not changing, it is horizontal only. You can say that convergence criteria is achieved. When the element number is 1, we got the value is equal to 0.21 approximately. When the element is number 2, in that case it is 0.23. When element number is 4, it is 0.235, and when the element number is 8, we got the maximum displacement at the tip, which is exactly equal to the analytical value, it is 0.238. Okay, so with this analysis we can conclude that when the discretization is better, that means when the mesh number is more, in that case you can find that our actual solution is very close to our theoretical solution. Okay, After that one, if you go for meshing again and again, the results will not change. The discretization, if you go with again and again, when the convergence criteria is achieved, if you go further discretization or if you make more numbers of elements, the result will not change. That is the condition of convergence criteria. Okay. So with this one, we will conclude our today's video. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.